Okay, in this video, we're going to take a look at various applications that use the whole idea, the concept of a ratio, to communicate information about different quantities. So I want to start out, first of all, just talking about a ratio and what it means, how we use it, and then just look at these different applications that make use of it. There's not a whole lot of calculations that we're going to be doing, but just to kind of get you familiar and using ratios to communicate information. So first of all, a ratio compares quantities in fraction form. So we're going to go back and be utilizing some of our fraction skills. It's usually given in reduced form. So you're going to be dividing both numerator and denominator by a common factor. But we're also going to make use of this whole notion that they use the same unit of measure, which brings me to just identifying how a rate is different than a ratio. Or a special type of ratio, at least. A rate involves different units of different measures, basically different variables, if you think about that. A common use of a rate would be, cost per ounce or cost per pound. The numerator here is given units of measure as, cost, money, dollars, whatever it might be. The denominator is in terms of weight. There's no way that you're going to get that in equal units of measure because they're measuring different variables. Another one that you're probably you're familiar with is miles per gallon. How we look at that as far as our gas mileage with our car, or another one, miles per hour. Okay, both of those utilize miles in the numerator, which is a measure of distance. Here, our denominator is liquid, gallons. We're not going to get miles, distance, and gallons in the same unit of measure because they're measuring different variables. And then same thing with miles per hour. Here, our denominator, we have time. But in each of these cases, we usually reduce this so that we have cost per 1 ounce, miles per 1 gallon, miles per 1 hour. And that's very typical of a rate. Very similar to what we're going to be dealing with a ratio. But with a ratio, you want to be careful that you are measuring two different measures of the same unit. In other words, both of them are measuring length. Both of those are measuring time, or whatever it might be. In this case, I've got an example, a ratio of 6 inches of waste for each 8 feet of wood. Let's suppose that this is a spec for a wood project. If you set up a ratio here of 6 inches of waste for 8 inches or 8 feet of wood, if you would cover up the units of measure there and just look at 6/8, reduce that, 3/4 of what you're purchasing is going to go to waste. That doesn't make sense. You're not going to invest in a project where you're wasting 3/4 of your material. So when we look closely at this, we realize that the numerator is in terms of inches, the denominator is in terms of feet. We need to get those in the same unit of measure. And we do that by knowing that every foot contains 12 inches. So we're going to multiply the denominator by 12 to get 96. So now we're comparing equal units of measure, 6 inches to 96 inches. This is what we mean by getting the same unit of measure. So now we recognize that both numerator and denominator can be divided by 6. So we're going to divide both numerator and denominator by 6, and we get to this reduced ratio of 1/16. And this is what we mean about getting it into reduced format so that you can actually make an easy evaluation here. 1 unit of waste for 16 units of wood purchased. Another way to communicate that is with this colon notation. You would read that as 1 to 16, a waste of 1 unit to 16 units purchased, or just writing out 1 to 16. So that's just the basics of utilizing a ratio to communicate information. Some different applications that use this, if we would go to a gear ratio of an engine, generally the gear ratio is given by the number of teeth on the driven gear compared to the number of teeth on the driving gear. So you can kind of set up a word ratio of driven over driving. So you're comparing driven to driving. E over I here. That's kind of a quick way to make sure that you get your order correct. So in this little drawing here, we have 48 teeth on this large driven gear, and we're speculating that we've got 20 on this smaller driving gear. So we can set up this ratio of 48 over 20. They're both multiples of 4, so we can divide both numerator and denominator by 4. So I'm going to kind of write that here just so that you know what I've done. 48 divided by 4 is 12. 20 divided by 4 is 5. So this has a 12 to 5 gear ratio. Another use of the gear or the ratio is when we're looking at pulleys, we compare the diameters of the two pulleys. The larger pulley here, I know that it's very vague, you can't really read that, but we have 120 centimeters to 40 centimeters on the smaller one. So when we set up this ratio of 120 over 40, they're both divisible by 10, so I can divide both numerator and denominator by 10. That eliminates my 0 there. And then I can recognize that they're both divisible by 4, so I have a 3 to 1 pulley ratio. Another use of ratios would be compression ratio. Looking at engines, you're looking at the maximum expansion volume compared to, this is a typo, compared to the minimum compression volume. A very common one, I guess, would be, I've seen it before, as a 10, 100 to 10 would be a 10 to 1 compression ratio. I'm not familiar with engine and piston ratios like this, but generally it's given as the expansion to compression ratio. Another very common use of ratios is the pitch or slope of a roof or a road. Any of you who have taken algebra probably recognize this whole phrase of rise over run is a common definition for slope, or the vertical distance over the horizontal distance. I'm going to write a word ratio here of rise over run. On this first one, we've got a rise, just this drawing here, we've got a rise of a roof that has 12 feet of rise for every 12 feet of run. So when you look at that 12 to 12, they're both divisible by 12, that's going to have a 1 to 1 ratio. 1 foot of rise for every 1 foot of run. Whereas when we come over here to this other example, the most extreme example that we have here, we've got 4 over 12. They're both divisible by 4, so that's going to be a 1 to 3 ratio. So in other words, a rise of 1 foot for every 3 feet of run. Another use of ratios in these two have to do with finances, the financial industry. The earning to debt ratio. Banks very often look at a person's monthly earnings compared to their monthly fixed debt that a person might be contracted to when offering credit. Generally, they like to look at a 3 to 1 ratio. This is just general. A lot of times banks have their own formula, but generally a 3 to 1 ratio is pretty common. That they're looking for every $3 that a household earns in a month, that they have no more than 1 that is contracted debt out. In other words, let's say you are bringing in $3,000 in your household every month, that they're hoping that you would have no more than $1,000 of debt contracted out in, that you're committed to, either rent, car payments, furniture payments, things that you've signed a contract and you are indebted to. They don't want to have anything more than that. If you would end up with having, say, only $2,000 coming in every month to every $1,000 coming out, that means you've only got about $1,000 left in discretionary spending, and that's a little bit of a tighter budget compared to once you take your $1,000 out of $3,000, having $2,000 left for discretionary spending. So that's just a general use of earning to debt ratio. It's used very common in the financial industry, and that's how you would interpret it. Another ratio in the financial industry is price earnings ratio. It's generally looking at the value of a stock divided by its dividends or its earnings. Let's say that you've purchased stock and each share costs $26, and over the course of a year, each of those shares of stock provided dividends of, say, $2. So that would reduce to a 13 to 1 price earnings ratio. Now, that would kind of depend. If you were in the process of building your nest egg, that would have a different meaning for you versus if you were living off of that nest egg that you need to live off that ratio. You'd probably look for a little lower ratio if you were living off of that. But again, that's financial use of ratios. Now this next one, mechanical advantage, involves the use of ratios with a hydraulic press, which I think is kind of magical. When you pull into your service station to have your tires checked or changed, or oil change and so forth, very often they'll use a hydraulic press to raise your car up. And basically the way that works is that there's a system, hydraulic system here, where pressure on this smaller piston here puts pressure down, and this fluid in here is very sensitive to this pressure, and it allows, basically through the system, it allows this car to be raised, which is a much heavier car. So you can identify and calculate the mechanical advantage of a hydraulic system by setting up a ratio, either of these ratios. First of all, I want to point out that this lowercase s in this lower right corner represents the force of the small piston. This lowercase l represents the force or weight of the large force here. So this S stands for the small piston, this L stands for the large. That's just a notation piece. Generally, in math, very often you identify a different component by this notation to the lower right. So I don't want you to get confused with that. You don't have to calculate or plug anything in for that. That's just a notation piece to say the weight of the smaller compared to the weight of the larger. Okay, the ratio for mechanical advantage is the force of the larger over the force of the smaller piston. That's one way you can calculate the mechanical advantage. So let's say that this car weighs 2,000 pounds. That's the force on my larger piston. Compared to, let's say all I have to do is put 100 pounds of pressure on this lower system, this lower piston, in order to raise this much, much heavier car. That's the beauty of the hydraulic fluid. I can reduce both numerator and denominator by 100. So I could reduce that, and I would say that this mechanical hydraulic system, the mechanical advantage of this hydraulic system, is a 20-to-1 ratio. In other words, this hydraulic press, this hydraulic system, can raise 20 pounds for every 1 pound applied on this hydraulic press. So I think that's kind of magical. Another way that you can calculate the mechanical advantage is to put the radius of the larger piston squared over the radius of the smaller piston squared. I don't want to get into that particular piece right now just because we'd have to square the radius, but I just want you to know that that's another way that you can calculate mechanical advantage. Okay, another use for ratio is to look at the scale factor with architect's drawings. Generally, architect's drawings, they have a ratio of a 1/4 inch of the drawing relates to 1 foot of actual distance. That's very common in architectural drawings. Again, we weren't doing a whole lot of calculating here other than setting up our ratios and then reducing, but I want you to notice that very often it was helpful to set up some kind of a word ratio to help us stay organized. So in this case, we set up the word ratio of the measure in the drawing compared to the actual. Here we set up kind of a symbol notation, force of the large over the force of the small. Up here I didn't write it out, but I could have written a ratio here of value to dividend. Here I could have written a ratio of earnings to debt. I'm just pointing that out, that very often it's going to be helpful to first write your word ratio and then put your information in place in order to reduce to the lowest terms.